This video is part 1 of a 3-part series focusing on 8th grade standard 8EE7, solving multi-step equations with variables on both sides, and recognizing the 3 types of solutions: one solution, infinitely many solutions, and no solution. In 6th grade, students will write and simplify expressions, as well as use substitution to determine whether a given number makes an equation true, which is key at the 8th grade level to check your solution. Then in 7th grade, students write and solve multi-step one-variable equations and equalities to include rational numbers, positive numbers, negative numbers, and the distributive property. However, the variable will only be on one side of the equation. In 8th grade, students continue to build on this understanding of solving multi-step equations and then move on to explain when these linear equations have one solution, no solution, and infinitely many solutions. Because 8th grade is the first time students are exposed to variables on both sides, it is very important to include the learning progression from concrete to representational to abstract to truly develop a conceptual understanding of solving equations. The focus strategy for this video is to use physical manipulatives in the form of algebra tiles to model the thought process behind solving equations with variables on both sides, in order to develop a conceptual understanding of what's actually happening in the problem. We will also explore key understandings such as zero pairs and properties of equality to show how that helps us to simplify expressions to solve the equations. Solving equations can be modeled in a variety of ways. In this video, we will explore using algebra tiles to model equations and expressions, as well as some of the key concepts of solving equations such as zero pairs and properties of equality. In part 2, we will follow up on visualizing what's occurring as you solve with the tiles. In part 3, we'll explicitly make the connection to the algebraic representation. You can represent the terms in an equation or in an expression with algebra tiles or by drawing the models to show the process. To represent any variable, in this case x, we will use the rectangular tiles. A long green tile represents positive x, and a red rectangular tile represents negative x. A value of 1 or a constant is represented with a small square unit tile. A positive 1 is represented with a yellow square tile, and a negative 1 is represented with a red square tile. So using that key, if you wanted to model positive 4x, you would need to use the x tiles. Because it's positive, you would use the green. 4 x's. Likewise, if you wanted to model negative 2x, again you would need the x tiles, but to denote its negative value, you need the red, so 2 x's. For positive 5, you will need to use the square unit tiles. Because it's positive, you will need the yellow, 5 positives. And for negative 2, again you'll use the unit tiles, but in red to show its negative value, for negative 2. We will use an equation mat to practice modeling this equation using the appropriate tiles. We will model the equation negative 3x plus 5 plus 2x is equal to x minus 4. On the left side, we have negative 3x, and we will use 3 negative red rectangular tiles. For positive 5, we will use 5 positive yellow square tiles. And for positive 2x, again we'll use our x tiles, but because it's positive, we'll use green. On the right side of the equation, we have x minus 4. For x, or 1x, we will use 1 positive green tile. For negative 4, we will use 4 negative red square tiles. Notice when we have the operation sign directly in front of the term, we use that to determine whether the term is positive or negative. Also notice when we have the variable x standing alone, it did not have a coefficient, but because it is still modeled with 1 tile, we can write it as 1x. Our second equation is 2x minus 5 is equal to negative 4x plus 3. Again, we'll model the left side first. For positive 2x, we will use 2 positive x tiles, and for negative 5, we will use 5 negative square tiles. On the right side of the equation, for negative 4x, we will use 4 negative x tiles. And for positive 3, we will use 3 yellow positive square tiles. One key concept we will repeatedly model in part 2 as we solve equations is the concept of zero pairs. We know that 1 plus negative 1 would equal 0. We can represent that using tiles, with a positive yellow square constant tile and a red square constant tile. Together, as a negative and a positive, they create a zero pair. A zero pair will essentially cancel each other out and disappear. The opposites in variables can also create a zero pair. Positive x and negative x. When added together, they create a zero, cancel each other out. This model will be a huge piece in solving equations in part 2. The final concept we will model with the tiles in order to solve our equations in part 2 is the property of equality, which allows us to add, subtract, multiply, or divide both sides of an equation by the same value and the equation remains balanced. Our first example here is 6 plus 2 is equal to 8, modeled with tiles. On the left side, if we consider taking away 4, if we on the right side do the same exact operation, take away 4, which is simply modeled by subtracting 4 on both sides, when we bring down our remaining values on the left side and bring down our remaining values on the right side, we can see that we still have a balanced equation. 4 is equal to 4. Likewise, if we consider the same equation, 6 plus 2 is equal to 8, and instead of subtracting, if we consider adding 6 to the left side and adding that same value of 6 to the right side, when we combine on the left side and bring down our values, we can see that we still have a balanced equation. 14 is equal to 14. In our last example, still using the equation 6 plus 2 is equal to 8, let's consider adding in a negative 6 on the left side. And of course, the same operation on the right side, adding in a negative 6. As we add in a negative 6 to both sides, we'll see that essentially that will end up looking like subtraction as we make our zero pairs and we match them up on the left side and we match them up on the right side. Our zero pairs will of course cancel each other out on the left, cancel each other out on the right. We bring down our remaining values, still leaving us with a balanced equation of 2 is equal to 2. In review, this video was part 1 in a 3-part series providing the context for representing and modeling the variables and constants in order to solve our multi-step equations with variables on both sides using algebra tiles.